Hello, I welcome you all in this presentation related with the subject materials processing fundamentals and practical, and we are talking about the metal casting, and in this particular presentation I will be talking about the various defects and issues caused by the unfavorable metallurgical transformations which will be happening in the casting during the solidification or after the solidification while the things are getting cooled to the room temperature. So, the major issues which includes like the gaseous defects. One is like the solubility of the gases, solubility of gases in liquid and solid state. If this solubility difference is too much, then it promotes the gaseous defects like porosity, blowholes like this, blowholes. Improper pouring means the temperature of the molten metal is not proper or it is not properly cleaned or filtered. Okay. So, these two things cause significant problems, especially with regard to the soundness of casting, particularly the cold shut and the misrun kind of the defects. On the other hand, if the impurities have not been cleaned, removed from the molten metal properly, then it will be promoting the inclusions, okay, or the dross that is coming with the molten metal. Okay. So, these are the two typically related with the like the molten metal. If we see the embrittlement or hard spot formation, if we talk of the transformation hardening metals like cast iron and steels, whenever these are cooled very rapidly, so rapid cooling, okay, especially after the solidification. After the solidification, when the rapid cooling is imposed, especially during the die casting or when excessive moisture is there, moisture in sand mold casting. So, the rapid cooling what it does, initially after the solidification, say if you are getting the austenite, due to the rapid cooling it will be forming the hard and brittle martensite in the especially at the casting surface, or it can be formed all across the section due to the rapid cooling, and that formation of the hard and brittle martensite leads to the increased hardness, but coupled with the reduced toughness, reduced ductility. So, these actually compromise very badly with their capabilities to withstand against the impact loading. Okay. Whenever this kind of the transformation occurs in a localized manner, okay, like say one section is very thick like this, another section is very thin. Okay. So, the thick sections will be experiencing the low cooling rate or slow cooling. On the other hand, the thin section will be experiencing the high cooling rate. So, this high cooling rate will be experiencing the transformation, martensitic transformation. But here due to the slow cooling, we may get the coarse perlite or ferrite kind of thing. So, this heavier section may not be experiencing any kind of the embrittlement, but the thinner sections may be experiencing this kind of the embrittlement or hard spot formation due to the rapid cooling in localized manner. So, embrittlement when it happens across the section, or localized hard spot formation due to the especially happens due to the presence of the very thin sections where from the heat is being extracted very rapidly. Okay. Another major metallurgical issue that is encountered in the castings, okay. So, that is also observed in case of the transformation hardenable metals, say high or medium carbon steels or cast irons. Whenever these are cooled rapidly and forming the martensitic structure coupled with the hardness of greater than 350 VHN. When hardness is more, martensite is being formed and the casting conditions are unfavorable with regard to the hydrogen. Hydrogen is getting diffused in the molten metal and then it is retained in the casting. So, hydrogen coupled with the martensite coupled with the high hardness of 350 VHN, okay, this combination becomes very sensitive for cracking, especially when the casting cools down to the room temperature and the development of the tensile residual stresses. So, in a casting, if the design is unfavorable, promoting the tensile residual stresses leading to the martensitic transformation due to the high hardenability and the rapid cooling rate, coupled with the high hardness of 350 VHN or more. Okay. And then, so if the residual stresses, martensitic formation, high hardness, if this is happening together, then this will and coupled with the hydrogen content, then this will be promoting the cracking even in the cold condition. Casting has been cooled down to the room temperature. So, depending upon the magnitude of the residual tensile stresses, depending upon the hardness or the amount of the hydrogen which is therein, cracking can occur immediately after the casting, or it can take really long for cracking to occur. So, therefore, it is very important that the residual tensile stresses are minimized, hardness is reduced, and the hydrogen content in the casting is minimized. Okay. Coming down to the next one, which is another metallurgical issue. This happens due to the unfavorable composition, especially when we have the composition such that it is leading to the formation of the wide solidification temperature range. So, if the composition being developed either due to the impurities or alloying content, okay, if the alloying is such that the solidification temperature range means the temperature difference between the liquidus and solidus, if this temperature difference is very wide, say greater than 50 then degree centigrade, then it will promote the tendency of the hot tearing or the cracking. So, sometimes even if the composition is not that unfavorable, but the cooling conditions are favoring to the segregation, leading to the increased presence of alloying elements in localized manner in certain areas and promoting the wider solidification temperature range in those zones, then it will be promoting the hot tearing or cracking in those areas. So, this hot cracking and or hot tearing is promoted especially in case of the ferrous metals. It is promoted by the presence of the low melting point elements like lead, phosphorus and sulfur, which is forming the compounds such that the solidification temperature range is enhanced. Most of the matrix is getting solidified at around say 1300 degrees centigrade, but the low melting point compounds are getting solidified at around 700 or 800 degrees centigrade. So, if that is happening, then the low melting point compounds will be segregating at the center, and there due to the development of residual stresses, cracking will be happening. Okay. So, it is important that either the presence of these impurities is limited to very low level, or the or the composition of the alloy is adjusted in such a way that the solidification temperature range is reduced. So, the cracking tendency is minimized. Okay. So, I have already talked about a lot of other things. So, here what we have to see here, the shrinkage defect. Okay. Shrinkage is one where the liquid is getting, during the solidification, liquid will transform into the solid. So, because of this transformation of the phase, there will be reduction in the volume. Okay. If the volume getting reduced is not compensated, volume of the metal which is getting reduced due to this transformation is not refilled or compensated properly by the molten metal which is to be fed from the riser. Riser will be feeding the molten metal desired to compensate the shrinkage occurring due to the transformation of liquid to solid. If this is not happening, then what will happen? Say initially we have filled the molten metal here, on the solidification at the top surface, what will be getting? We will be getting a depression like this, solidified casting. So, this kind of the unfilled section at the top will be observed due to the shrinkage of the molten metal on due to the transformation from liquid to solid, but this zone which should have been refilled or compensated by the supply of the molten metal from the riser, that could not happen, then it will be leading to the this kind of the defect. Okay. This is particularly promoted when the solidification is not proper, or the gating system is not designed properly, or inadequate riser is not able to feed the molten metal properly, or sudden change in cross section in certain areas is taking place, that is blocking the Like say if there is a great difference, okay, in this, like here it is going like this. So, if we are feeding the molten metal like this, so molten metal is being fed from here. So, here it will be filling, then it will be passing through this zone, and then this zone will be filled in. But if this section where its thickness is less, if it gets solidified first, then it will be blocking the supply of the molten metal in the other areas, and that can lead to the lack of supply of the molten metal in other sections, leading to the defects like misrun. Okay. So, and the pouring temperature is not proper, means the low temperature of the molten metal. If the temperature of the molten metal is low, then viscosity will be high, surface tension will be high, and that will reduce the fluidity. And if the fluidity is reduced, then it will not be able to the flow through the finer channels properly, and it will take long time to fill the things. Okay. So, this is the typical defect which is observed. The porosity in castings we find of the two types. One is the gaseous porosity and another is the shrinkage porosity. So, shrinkage porosity, the gaseous porosity, whenever it is observed in a casting, it is of the spherical family, because the molten metal tries to take the minimum possible shape, or these gases try to take the minimum possible shape with the minimum possible surface area. So, that becomes the of spherical family. But when we find that the molten metal is not able to reach in the interdendritic arm spacing, you see, like say this is the casting and the things are getting solidified from all the sides. So, it is possible like the few the dendrites which have solidified, it is fine, but in between if due to the shrinkage some gap is left unfilled, then that will cannot be filled due to the limited ability of the molten metal to fill those gaps, or limited or blocked channels for the flow of the molten metal. Okay. So, this can happen especially when the shrinkage porosity can happen. So, shrinkage porosity is typical of the dendrite morphology. This is one, this is how we can identify it, and this happens especially when the solidification is not directional. It is not starting from one end and progressing to other, but it is maybe progressing from the different directions and leading to the unfilled sections somewhere in between. Okay. And this can also happen due to the improper gating system, say leading to the very longer time for the solidification, longer time for filling the mold cavity. In meantime, there is a significant reduction in the temperature of the molten metal. A riser which is there to feed or compensate the shrinkage is not able to supply the desired amount of the molten metal, or the temperature of the molten metal is very less, leading to the increased viscosity and surface tension. So, the fluidity is getting reduced, and therefore molten metal is not able to flow through the channels which are there for the flow of the molten metal, or abrupt change in section of the casting is taking place, leading to the blockage of the molten metal. There are two main reasons behind the improper pouring that leads to the development of defect in casting, and these two aspects related with the improper pouring are like incorrect temperature of the molten metal. This is one, or the second is the presence of the impurities, dross, flux, or other impurities which should not be there in the molten metal. So, this particularly happens due to the limited or very poor filtration and improper control over the temperature that leads to the. So, these are the two aspects that basically are responsible to the various types of defect due to the improper pouring as far as the molten metal is concerned. The second aspect is like how turbulent flow is taking place due to the turbulence in the molten metal. So, this is the another aspect. So, especially the incorrect temperature causes multiple problems. For example, the misrun and cold shut, these are the two main problems which are caused by the incorrect temperature of the molten metal, or any other factor which is cooling the molten metal very rapidly will be promoting the misrun and cold shut. Say die casting, the metallic mold, or in the sand mold casting very high percentage of the moisture. So, these are the two aspects which will be affecting or which will be causing the very high cooling rate and leading to the misrun or cold shut kind of the defect. That will be working in the same way as that of the low temperature of the molten metal. Okay. And improper filtration of the molten metal or removal of the impurities will be leading to the supply of the molten metal to the mold with the impurities, dross and other oxides etc., coming with the molten metal. Okay. While the turbulence will be encouraging the pickup of the gases by the molten metal from the atmospheric air. So, that will be promoting the porosity and the presence of the inclusions as oxides if these are being formed, or the dissolved gases which will be contributing towards the other issues in the castings, about which we will be talking little later. Okay. So, as far as the improper pouring is concerned, the temperature is one, cleanliness of the metal is another, and turbulence of the molten metal is third. Okay. These are three important aspects. So, when the temperature of the molten metal is not proper, either it is very high. So, when a very high temperature means it will be promoting the defects like penetration in the sand mold, okay, in soldering in case of the die casting. Soldering in case of the die. Soldering is what? Where the metal of the casting tends to stick with the surface of the mold due to the high temperature or interaction of the molten metal with the die surface. Okay. So, this is the another one. On the other hand, we will see that if the temperature is low, molten metal temperature is low, then this will be increasing the surface tension and it will be increasing the viscosity, which in turn will be reducing the fluidity. This will make the this will increase the time required for filling the mold cavity. This is one, and this also can bring a situation where the solidification can start even before completely filling of the mold cavity. So, if that happens wherein the molten metal is not able to fill the mold cavity completely and solidification starts, or the molten metal is not able to reach especially the fine sections of the mold, then it will be leading to the defect like misrun. Okay. So, the misrun is the kind of defect that will be primarily caused by the low fluidity increased by the high surface tension and viscosity due to the low temperature. This is one. Similarly, the high cooling rate which is experienced by the molten metal during the flow through the gating system or in the mold, then that also has the similar kind of the effect. High cooling rate will be reducing the temperature very rapidly, which in turn will be increasing the surface tension viscosity, reducing the fluidity, and which in turn will be increasing the time for filling the mold cavity, and that in turn will be promoting the cold shut and the misrun kind of the defects. Okay. So, the major problem comes because of the low temperature or low temperature of the molten metal of the melt, okay, or very high cooling rate that is experienced. So, what are these conditions? Like if the molten metal temperature is not controlled properly, then it will can occur, and if the cooling is very fast like in the die casting where the metallic mold is used, or the moisture content with the sand mold is very high. Okay. If the sand mold is high, then both these will be promoting the high cooling rate. High cooling rate means the lower temperature and reduced fluidity, which in turn will take longer time to fill the mold cavity, or that in turn will also be increasing the defects like misrun and cold shut. Okay. So, these two kind of the defects, the misrun is one in a completely filled cavity or unfilled cavity, like say a mold having multiple thin sections like this. So, some of the sections which are very thin where molten metal the low fluidity and high viscosity surface tension is not able to get into. So, those sections will be left unfilled, means we will be getting the casting of the shape which is not really desired. Okay. And the cold shut is a kind of defect where in the large size castings, if the molten metal is being fed from the different directions, okay, like say these are the two different directions. So, the molten metal stream will be coming from the two sides. In meantime, if the heat is extracted very rapidly and the temperature of the molten metal coming from the two sides, the two streams of the molten metal which are coming from the different sides are of very low temperature, then they will not be fusing together and they will be leaving behind an interface between them, and this interface will not have any kind of the metallurgical bond, and that will act as a weak location where from the casting will break. Okay. So, the cold shut is formed when the two different streams of the molten metal coming from the different directions do not fuse together, leading to the formation of an interface. Okay. So, this is a kind of the lack of bonding in the different sections formed by the streams coming from the different sides. These two are encouraged by the low fluidity, obviously due to the low temperature. Okay. Two small sections where the fluidity must be high to penetrate the molten metal, to be penetrated by the molten metal. So, if the temperature is high, then surface tension and viscosity will be less, and viscosity will be less and fluidity will be high. So, even thin sections will be easily penetrated, but if it is not the case, then it will be difficult for the molten metal to penetrate and get into those fine zones. Okay. High heat transfer rate means the high cooling rate. If the cooling rate is high, then the rapid cooling of the molten metal will be lowering the temperature, and that in turn will be leading to the misrun and cold shut, both kind of defects, and this particularly happens when the surface to volume ratio of some of the sections of casting are very high. I will give example, like say if the section, this is the kind of the geometry. So, here for this section the surface to volume ratio is like higher as compared to is lower as compared to the another zone. If we see S by V ratio for this section is very high, means heat from the molten metal will be extracted very rapidly as compared to the another section where S by ratio is less. So, if S by V ratio, surface area to the volume ratio is less, then it will take long time for heat to dissipate to complete the solidification as compared to the case when the S by V ratio is high. Okay. So, the rapid heat transfer is facilitated by the casting or its sections when the surface area to volume ratio is very high, and this kind of situation is also encouraged by the green sand mold having the high percentage of the moisture, or the metallic molds where the thermal conductivity of the metal mold is very high and extracting the heat very rapidly. So, the third aspect related with the defects due to the improper pouring is that improper filtration or removal of the impurities, that will be leading to the defects in form of inclusions or impurities going with the molten metal into the mold and encouraging the casting. So, like impurities like sand and other impurities which are getting into the mold, that happens due to the improper filtration or improper gating system design. Then the defects due to the unfavorable metallurgical transformation, this is one of the very major challenge, especially when the impurities present in the certain kind of the impurities are present in the alloy which are promoting the solidification temperature range. You see, either alloying or impurities, if they are increasing the solidification temperature range, like say greater than 50, then that will be increasing the tendency of the hot tearing or hot cracking. Okay. So, let us see that what it is. So, hot tearing or hot cracking, hot tearing, hot cracking or tearing, this occurs at the terminal stage of the solidification. Terminal stage of solidification, this is one. So, this is occurring means the last stage of solidification, this is one, and this will be occurring especially when the tensile residual stresses develop in the solidified portion of the casting, which is shrinking, leading to the development of the tensile residual stresses. So, if we have a situation where still we have the liquid molten metal which is yet to solidify in very localized manner, but there is also presence of the tensile residual stresses. This happens when the solidification temperature range is very wide. So, wherever the impurities are getting segregated or alloying elements are getting segregated, that will be the region where the liquid metal of the low melting point will be left at the end to solidify, and there if the tensile residual stresses develop, then that will be promoting the cracking. Okay. So, if we talk of the ferrous metals, impurities like phosphorus, sulfur and lead, these are commonly found in the ferrous metals, and if their percentage is greater than 0.05, then this promotes the formation of the iron sulfides having very low melting point, increasing the solidification temperature range and promoting the hot cracking or hot tearing kind of the possibilities. Because if the solid state shrinkage is taking place, then that will be developing some kind of the residual stresses in any case, maybe in localized manner. So, if we have tensile residual stresses coupled with the wider solidification temperature range, then this will certainly promote the solidification, sorry, this the hot tearing or cracking tendency. Okay. This is one aspect. Another one, sometimes the alloying concentration is such that alloying elements or the composition of the alloy is such that is promoting the wider solidification temperature range. Okay. So, how this happen? Let us say, let us talk about a particular kind of the alloy which is having the partial solid solubility like this. Okay. Here in y axis we have temperature, in x axis we have say composition A and B, right. So, here say this is B and this is alpha, alpha plus liquid, and this is beta, beta plus liquid, this is beta, and here we have alpha plus beta, and here alpha plus beta like this is eutectic, and this is beta plus alpha plus beta like this. So, if we see here for this particular composition, so in this phase diagram, say having the partial solid solubility in the solid state, this is the liquidus, okay, this is the eutectic point, and this is the solidus, all this is solidus, right, this is solidus. So, if we see the gap between the liquidus and the solidus is maximum where, for this particular composition or for this particular composition. So, if the composition of the alloy is such that solidification temperature range is very wide, then certainly it is going to promote the hot cracking or hot tearing because of the wide solidification temperature range. There will be there will be a liquid metal which will be left to solidify at the end, and while the residual tensile stresses will be developing in the solidified portion, okay, due to the cooling from the solidus to the room temperature. Okay. So, if this is the composition where the solidification temperature range is, say here this is the solidification temperature range, this is for this particular composition. So, by adding the alloying elements such that this solidification temperature range is minimized like this. So, this is narrow, or by adjusting the composition of the alloy, the solidification temperature range can be adjusted, and somehow if we can reduce the solidification temperature range, then this will reduce the tendency for the hot cracking. Okay. This will reduce the tendency of the hot cracking. This is one way. Another way is that add such kind of the alloying elements which will help to avoid the formation of the low melting point constituents. If this is the case, then also the wider solidification temperature range can be reduced, wide solidification temperature range situation can be reduced, and that in turn will help in the reducing the tendency of the hot cracking. So, hot tears basically or hot cracking basically occurs due to the tensile residual stresses caused by the shrinkage, okay, and in the alloy having the wider solidification temperature range, and especially if the tensile residual stresses and coupled with the wider solidification temperature range, and if this is clubbed with the low strength of the alloy at high temperature, then certainly this is going to promote the cracking. Okay. So, what are the causes for which are leading to this kind of situation? Poor casting design and resulting in the abrupt change in the cross section without proper fillet. This will be promoting the stress concentration being set up due to the shrinkage. Okay. poor collapsibility of the mold, if or too hard ramming is done, then this when the solidified casting is shrinking, it will not shrink because of the poor collapsibility, or ramming is too hard, then this will also set the residual tensile stresses. Okay. Or impurities or alloying concentration is such that it is forming the low melting point constituents, like there is a lead. So, lead is having very low melting point, or if the sulfur is there, it is reacting with the iron to form iron sulfide, again leading to the formation of low melting point iron sulfide, then this is going to promote the wider solidification temperature range, because normal steel may be solidifying at 1300 degrees centigrade, but this will solidify at say 750 or 800 degrees centigrade. So, this will be promoting the solidification temperature range significantly, and therefore, it will be promoting the cracking. So, if somehow we can avoid the formation of iron sulfide. So, what we can do in the ferrous metals having the higher percentage of the sulfur, if we add manganese, then manganese having the greater affinity with the sulfur, forming the manganese sulfide, which is of a relatively higher melting point than the iron sulfide, and therefore, solidification temperature range is minimized, and that in turn reduces the cracking tendency or hot cracking tendency. The same is true for the aluminum alloys. Aluminum alloys are very sensitive for cracking. Say if we consider this one, this was in x axis we have the alloying concentration, in y axis we are having the hot cracking tendency. Okay. So, for this percentage of the aluminum copper combination, okay, what we see, the cracking tendency is maximum, then it is coming down. For aluminum magnesium system, the cracking tendency is maximum here for this 1 percentage of the magnesium. Similarly, for aluminum silicon system, around 1 percentage of the silicon, the aluminum 1% silicon will show the maximum hot cracking tendency. Why? Because this is showing the widest solidification temperature range and resulting in the increased hot cracking tendency. So, what is the way out? If somehow it is possible to adjust the composition of these alloys either towards the left or towards the right, then we will be having the lesser solidification temperature range and reduced hot cracking tendency. So, the best way is to adjust the composition of alloy or reduce the impurities. Okay. So, the solidification temperature range is minimized and hot cracking tendency is reduced. This is showing the typical case for the aluminum, copper, magnesium system. So, how the cracking tendency is affected, like say in x axis we have the copper and y axis we have magnesium. So, for this particular say 2% of the copper and 1.5% of the magnesium, we are having the maximum cracking tendency like this, resulting in the largest crack length that is produced. And as we adjust the composition of the magnesium and the copper, then cracking tendency is minimized. So, if we have the magnesium greater than this much percentage of 4 or copper greater than 4%, then we will be having the no cracking zone. Okay. So, we need to adjust the composition of either singly or in combination of magnesium and copper such that we land or composition of the alloy is of the no crack sensitive zone. Okay. Now, the another major problem that is caused in terms of the cracking is caused by the metallurgical reactions, especially in case of the hardenable ferrous metals. Hardenable ferrous metals like the cast iron, high carbon steels, okay, and lot of steels which show the carbon equivalent greater than 0.4, they show greater the hardenability. Okay. So, what happens when these systems in the castings, when these systems are used for casting, you see the surface gets chilled. Okay. So, if we are using the die casting, then certainly this is going to get quenched. Okay. On quenching, what we get on very rapid cooling of the systems having the carbon equivalent greater than 0.4, what we get basically high cooling rate will be promoting the formation of the martensite as per the continuous cooling transformation diagram. So, we have to just refer as per the composition, refer the corresponding continuous cooling transformation diagram to see what it will be forming under the very rapid cooling or slow cooling. In sand mold casting, what we get very slow cooling rate, and that is why we get the coarse perlite. Somewhat higher cooling rate is achieved if then that will lead to the fine perlite. Very high cooling rate will be resulting in, say, this is for this particularly true for the eutectoid. You see, eutectoid steel means steel of the 0.8% carbon. Okay. Similarly, so in the castings, if the carbon equivalent is high, say greater than 0.4, then what it will be doing? Rapid cooling will be promoting the martensite or mixture of perlite and martensite. Okay, if this is happening, then our hardness will be enhanced significantly, and the toughness and the ductility will be reduced drastically. If that is happening, then the ability of the casting to take the impact load is compromised very badly. Okay, this is one aspect. The second aspect is where, like, the section size is varying. Somewhere it is very thick and somewhere it is very thin. If there are few thin sections and few thick sections, so thick sections will be cooled slowly, slow cooling in thick sections, and thin sections will be cooled rapidly. High cooling rate will be experienced. So, it is possible heavy sections will be having the fine perlite and thin sections will be having the either martensite or mixture of perlite and the martensite. Okay. So, wherever the martensite is being formed, our hardness will be extremely high. Okay, that will show the embrittlement or very low toughness as compared to the heavy sections which will be experiencing the low cooling rate. Okay. So, the cast iron and steel castings, these basically suffer the embrittlement or hard spot formation in localized manner. This happens due to the uncontrolled metallurgical transformation, especially formation of the martensite, especially in the ferrous systems or hardenable systems having the carbon equivalent greater than 0.4. Okay. So, this happens especially in the cooling rate experienced is very experienced by the molten metal is very high, and this may happen due to the die casting. In case of the die casting, where the metallic molds are used offering the higher cooling rate, or the sand mold having the too high moisture. So, improper design of the die, in that case, like say the cooling rate, very high cooling rate will be experienced by the dies. Hard spots, wherever it is formed, that will make the machining difficult because of the excessively high hardness of the system. Now, I will summarize this presentation. In this presentation, basically I have talked about the major issues which are experienced in the casting due to the unfavorable metallurgical transformation. Thank you for your attention.